The SPHERES satellites fly aboard the International Space Station, so we can learn more about how to control satellites. Specifically, how can we learn how multiple satellites work together instead of just one satellite at a time? With this, we can do future things like in-space robotic assembly. Instead of needing to send a bunch of space shuttles, which we don't have anymore, to build the next space station or the next interplanetary transport vehicle like going to Mars, we want to learn how can we get satellites working together to do all that assembly so that we don't send humans every time. We send a bunch of robots, they assemble the next big thing, and then we send humans when the next big thing is ready to go. That should make it a lot cheaper and a lot safer, and should be able to do it with all the resources we currently have in the plans for future space exploration. The SPHERES satellites are nanosatellites aboard the International Space Station. They're designed to fly only inside. They look like little volleyballs. They're about 20 centimeters in diameter. They're pretty massive. They're almost 4 kilograms, but they're in space, so they don't weigh, right? They're 4 kilogram masses floating around. And we designed them with the idea of being able to test a lot of different things in space station. So we did not advance the technology of the satellite itself very much. Actually, to the opposite, we used very common technology. One of the things we're very proud of is that the majority of our propulsion system is based on either a little bit of medical devices, which is just the tubing is what is used in the medical device world. And the pressure tank is actually the same tank that you would use when you're going to paintball. If you go play paintball, the same tank we send up to space. It's very safe, and we're very happy to have done a project that uses normal technology up to space station in many ways. There are some custom things, like what we call the metrology system. Metrology means knowing where you are, basically. So that is a custom system. It uses a combination of infrared and ultrasound signals to triangulate the location of the satellite. And then we have a computer called a digital signal processor. So it's processing digital signals, creating from all this, to know where it is and determine what thrusters to fire so that it knows how to move. So basically, you have this little satellite about this size that can move all around our dedicated area inside space station in every direction that we want it to. And at the same time, we designed it so that the thrust is small enough that there are no safety concerns on what the satellite is doing. It will never be able to go faster and have contact with anything in space station of any forces higher than an astronaut pushing themselves off a wall. So our satellites are very agile, and yet they're weak enough to never present a safety issue, and that's why we can do many different things with them. We have about 6 to 8 different type of projects. We've done a pretty nice results on formation flight, when the satellites are maintaining a formation, when they're doing things like collision avoidance, making sure that as the formation changes, so sometimes the satellites are in a straight line, but if they change formation as they move around, they don't collide to each other. That's been a really successful work so far. We've also done some very interesting docking maneuvers. In other words, the satellites separate apart, coming together, that not only coming together straight next to each other, which other people have done before. The amazing thing of the project working inside space station is we can do risky things. We can try things that you would not try with a real satellite out on space, because you're going to be worried about losing it. Inside space station, we have one satellite rotating, spinning around, and the other one docking to it. And we can try it multiple times. It actually worked on the second try, which we're really happy about. But even if it didn't, we can try it multiple times over and over again. And we're doing all of that in true microgravity, full 6 degrees of freedom. So when the satellites can move out in any direction, we can still try it and show that the algorithms that we're using to dock our satellites are reasonably advanced to be able to work in the future on real big missions. So those are some of our very interesting results so far. The last set of results we have from this year, kind of fresh out of the space station, is on vision-based navigation. So using cameras to detect the presence of other satellites and to be able to dock to other satellites with cameras. So we're just starting that research. But we have some very interesting things going on where we can make one satellite turn in ways that we cannot make them turn in the Earth because they're floating, and be able to really identify all that motion of the satellites just with cameras without any other sensor. From the perspective of in-space robotic assembly and servicing, we will benefit in the Earth by making it easier and cheaper to get new communication satellites, to upgrade satellites in space that let us have a much better life on Earth, right? We depend a lot on satellites today, so we want to understand how to get them better and cheaper every time. And from the exploration side, we are hoping that we're helping keep the whole idea of space exploration alive as one of those top things that humans want to do, which is exploration. So that we keep the society knowing that, yes, we're still at the forefront of researching beyond Earth.